Welcome back, students. Let's go back to section 3, and this time let's complete it. We talked about the chain rule and went through some elementary chain rule problems, and then a little bit more difficult problems that you have to combine several chain rules or the chain rule and other rules together. And now let's talk about second derivative problems. Second derivative, how bad can it be? Simply taking the derivative once more, but sometimes that can be pain in the rear end. For example, if you have something like this, okay, in that case, taking the derivative is easy. (15x to the fourth power minus 10x minus 4, that's the derivative function, isn't it? Just a power rule. And then another power rule, f double prime of x, multiply, then 15 times 4, so that's 60, x to the third power, minus 10, and that's it. And then if you take the third derivative, and that's 180x squared, and so on. This kind of computation is not too bad, but that's because we use only the power rule. In this case, things will not be that simple. Let's take the derivative. Well, this is an exponential function, so it always stays the same. And then the by chain rule, inside always stays the same. And then we multiply the derivative of the inside, right? What's the derivative of the inside? That's 6x minus 2. So if I simplify, you get 6x minus 2 times the exponential. Most of the time I do not simplify, but this time it was necessary because this is not the end of the problem. I'm going to take another derivative because I want to take the second derivative, and for that purpose I took a bit of simplification so that the second computation is a bit easier. Okay, here we go. We have a product rule now. First function times the second function. Previously no product rule, but after chain rule we ended up with something coming, so we ended up with a product rule, and that's pretty natural. For the second derivative problems, product rule pop out of nowhere. Not out of nowhere, as a matter of fact. It came from the chain rule of the previous problem. Anyway, here you go. U prime and V, the same thing here. Plus U and then V prime. Exponentials stay the same. And then, by the chain rule, we have to multiply the derivative of the inside. And the derivative of the inside is 6x minus 2. So if I simplify, what do you get? Well, let's see. Exponential is common. Oops. Exponential is common. And then 6 plus 6x minus 2 squared. Looks like that's what I'm going to get. Did I do this right? And of course, if I break up this parentheses and take the like terms together, I may get a little bit simpler expression here, but I'd rather stop here. I mean, I could have stopped here in the first line too. In any case, the key is the product rule shows up out of nowhere. Chain rule, and then product rule, and then chain rule. Here, when you calculate V prime of the product rule, the chain rule applied. Here's the answer key. Oh, okay. I did further manipulation. Broke up all those parentheses and ended up with this expression here. Okay, all right. Now, how about the next problem here? The derivative of this is, well, we have logarithmic function, so 1 over whatever, and by the chain rule, nothing changes inside. So same thing here, and we have to multiply the derivative of the inside. That's a chain rule, isn't it? What's the derivative of the inside? 4y cubed plus 6y. And if I simplify, I'm going to get this. 4y cubed plus 6y over y to the 4th power plus 3y squared. Did I do this right? That's how you handle the logarithmic function. Whatever inside goes to the denominator because the derivative of the log function is 1 over that. And by the chain rule, nothing changes inside, but we multiply the derivative of the inside. So what usually happens is a derivative over the inside. Now let's go to the second derivative. Now we don't have to deal with the logarithmic function. That's the good news. And the bad news is we have a quotient rule. Well, it's not too bad. Quotient rule is not too bad. Let's just copy and paste. And then denominator squared. And then we have to do u prime v minus uv prime. So u prime, the derivative of the numerator, a little bit bigger font. The derivative of the numerator here, u prime. So that's 12y squared plus 6. And then v, the denominator, minus u and then the derivative of the denominator, v prime, 4y cubed plus 6y. Looks like that completes the problem. U prime v minus u v prime. The prime part, I'm using brackets to emphasize that this is a derivative computation. For the parenthesis part, it's just copying and pasting. Here's the answer key. Yes, indeed, the same thing. Let's see, how about some tangency problems? Okay, basically this is what we want. Plug in the x0 values for y0, and then take the derivative, and then plug in the x0 value for the slope. If you have the slope, then you can put everything into this form, the slope point equation of the line. Alright, how do you get y0? By plugging x equal to -1. That's easy. After taking the derivative using the chain rule, you can plug in x equal to -1 to get the slope. Here we go. Straight up plugging in, then you get the y0 value. Now here's the derivative computation. The chain rule. In order to plug in the numbers a little bit more effectively, I changed everything into traditional form, but that's not really necessary. You could have used calculator. And then plug in the numbers and we get 1 over square root of 2. That's the slope. In the end, we get this. Slope, y0, and we have slope point equation of the line. Right there. How about the next problem? Well, try it on your own. Stop the playback and try it on your own. Same idea, right? plug in the x value to find out the y0 value, and then take the derivative, and then plug in the x value to get slope. There you go. Straight up plugging in, and we get log of 3. That's your y0 value. Now the derivative, okay, we have this thing going to denominator, and then multiply the derivative of the inside. So we get this over that. Alright, and then plug in the numbers and do your simplification. You get m equals to 2. That's the slope. In the end, we get this slope point equation of the line. Okay, so much for section 3.